Hello students, welcome to the class. So in the previous class we have discussed about the electronic configuration, that is filling up of the electrons into the various orbitals. We know that maximum number of electrons present in an orbital is given is equal to 2. For orbits it differs. Yes, for s orbital, for orbit we say it as 2n square, right? So for orbital it is 2. So how to fill up the electrons? We have seen the principle where there are three rules for filling up of the electrons. Aufbau principle. In the ground state of the orbitals of the atoms, electrons are filled in the increasing order of their atomic, in increasing order of their energies, right? And energies, it is being governed by, we have seen n plus L rule also. Lower the value of n plus L, lower is the energy, and that orbital is written first. But if the n plus value is same for two different orbitals, then we'll see the n value. Lower the value of n, lower will be the energy. So this we have seen in Aufbau principle. Further, how to fill the electrons, and you need not remember calculate n plus L rule for all of them. You just have to remember this particular format: 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. Yes, this is how we write the fill the electrons in the order of increasing energies. Pauli's exclusion principle we have seen, which says no two electrons in an atom will have all four quantum numbers same. Even if principal azimuthal quantum numbers, magnetic quantum numbers are same, the spins will be different. Therefore, in the other way, you can say only two electrons may exist in a same orbital, and these two electrons must and should have opposite spin. If there are only two electrons can be present in an orbital, and if there are those two electrons, one will have plus half spin, that is clockwise direction, and another one will have minus half spin, that is anti-clockwise direction, which is shown either like this or like this, and here you show it like this or like this. Yes, and those two electrons in the orbital are represented either like this, or you can represent them like this. You need not get confused. Anyhow, we can use the format. Hund's rule of maximum multiplicity: pairing of the atomic orbitals takes place only when the orbitals are singly occupied. For S subshell, we have only one orbital, m value, there is only one m value. For P subshell, there are three values. So there are three orbitals. You can call them Px, Py, Pz. And for D, there are like that five. 1, 2, 3, 4, 5. So if I say there are two electrons in p orbital, then I cannot write it like this. Yes, how I need to write, how I need to mention? Yes, first I have to fill the electrons here, then here I have to fill. If it is 3, I'll write it here. If it is 4, after filling the 3, I will use this one. If it is 5, first I'll fill all the 3 orbitals, then I will go for pairing. So it says pairing of the orbitals does not take place until and unless all the orbitals are halfly occupied. Similarly with D. So if it is D2, I will write it here. D3 here. 4 here. 5 here. Yes. 6, sorry, this is only 5. This is only 5. D has 5 orientations, so 5 orbitals. If it is 6, then pairing starts. 7, 8, 9, 10. And D subshell has got 10 electrons. So this was what we had discussed. So using this, we write the electronic configuration of the atom. So what is electronic configuration? Distribution of the electrons into the orbitals of an atom is called its electronic configuration. And this electronic configuration, it is written in two ways. S raised to A, P raised to B, D raised to C. That means S, P, D represent the orbitals. A, B, C represent the number of electrons. Orbital diagram, you can either use this orbital diagram. So here what I wanted to discuss is, we'll discuss some of the examples. Here I will mention atomic number, then element symbol, then we will write electronic configuration, orbital diagram. Let us see. Okay. Okay. So atomic number you denote it by Z, right? So first, what is the element? It is hydrogen. We'll take some of the examples. Symbol is H. Electronic configuration. As we have discussed, we will follow all the rules and write the configuration. So first comes 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, I'm sorry, 5s, 5p, 5d, 4f, 5f, like this, and we will show them the arrow marks in which we are going to progress. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4s, 4p, 5s, 4, then this, it continues, right? So electrons are filled in this manner. So here 1s means hydrogen. How atomic number is 1 means how many electrons? 1 electrons. So 1s, 1 electron. Or I can show orbital diagram. So this is yes, and I will show the electron here. Second, helium, He. So what is the configuration? 1s2. We write it like this. Arrow mark down. 3, lithium, Li, 1s2. After 1s comes 2s. Here 2 electrons are used. Here one more. So 1s, sorry, upward and then downward, or you can write vice versa and upward. 4, beryllium, B, 1s2, 2s2, 4 electrons. So here I have a spin up, spin down, spin up, spin down. Fifth one, boron, beryllium is Be, boron is B, 1s2, 2s2, 2p, 1. So 2 plus 2 plus 1 is 5. So here we have 1s, spin up, spin down, 2s, spin up, spin down, 2 electrons. P, there are 3 subshell orbitals, but there is only 1 electron. Carbon, C, 1s2, 2s2, 2p2. So 1s2, 2s2, and 2p2 how we'll write? We'll follow Hund's rule of maximum multiplicity. So we'll write it. Pairing will not take place until each orbital is singly occupied. After carbon comes nitrogen, 1s2, 2s2, 2p3. So here 1s2, then 2s2, 2p3. So singly occupied first. Eighth one, oxygen, O, 1s2, 2s2, 2p4. One only till 10 electrons are elements I will show. Later you can practice it. 2p4. So spin up, spin up, spin up, and then pairing starts. Ninth one, fluorine, F, 1s2, 2s2, 2p5. So orbital diagram, spin up, spin down, spin up, spin down, and here spin up, spin up, spin up, spin down, 5 electrons. 10th one is neon, Ne, 1s2, 2s2, 2p6. So here we have spin up, spin down, spin up, spin down. Third one, spin up, spin up, spin up, spin down, and spin down. Yes, so this is how, this is electronic configuration. This is another way, that is orbital diagram. So this is how we represent the electronic configurations. That is explanation for electronic configuration, right? Okay. There is one more way of representing the electrons. The other way of representing the electrons is, I will tell you. Okay. Now see here, example of sodium I'll consider. Sodium atomic number is 11. So electronic configuration comes to 1s2, 2s2, 2p6, 3s1. 6 plus 2 plus 2, 10 plus 1, 11. So when you look, this becomes the outermost shell. Here, this is the outermost shell. So this is the only shell here, so I'll not worry. In this case, this is the outermost shell. Here, this is the outermost shell. In this case, 2s, 2p is the outermost shell. Same here, 2s2p, 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 2s2p is the outermost shell. So outermost shell has got how many electrons here? 1. Here 2 electrons, here 3, here 4, here 5, here 6, 7, 8. Understanding? Here outermost shell has got how many electrons? This becomes the outermost shell. So it is having 1 electron. If you look at, so outermost shell is called valence shell. The outermost shell is called valence shell, and the electrons in valence shell are called valence electrons. Valence electrons. So outermost shell in some cases will be incomplete. Can you see here? S should have 2 electrons, but it is having only 1. So it will be incomplete. Even third shell has got S, P, D orbitals, right? So it is only S with 1 electron. But if you look at the inner shells which are present, all are completely filled. Yes. How many electrons are there? 10. Just like our neon with 10 electrons. Can you see? It is same as neon. So I can write the electronic configuration of sodium as inner shell configuration. We call it as core configuration. So that core configuration is regarding what? It is noble gas. So I will call it as noble gas core or configuration. Noble gas core or configuration. So how do I represent? I will write the noble gas, previous noble gas, and its atomic number is 10, plus outermost shell. I will represent it like this, 3s1. Are you all understanding? So this is another way of writing the electronic configuration. How? Representing the noble gas configuration into the box, writing the atomic number here and writing the valence shell here. Yes, understanding? So this is another way of representing the electronic configuration. Another way of representing the electronic configuration. And this way of representing the electronic configuration is called condensed electronic configuration. Condensed electronic configuration. Did you all get it? Yes, condensed electronic configuration. Same, one more example you take, magnesium. Yes, magnesium, atomic number 12. So it comes 1s2, 2s2, 2p6, 3s2. Yes, don't come to the conclusion that it is having completely filled. Third shell is not only having s orbital, it is having p and d. But p and d are what? They are 0. There are no electrons. Aluminium, it is 13. 1s2, 2s2, 2p6, 3s2, 3p1. So this is the outermost shell here. Yes, it is the outermost shell. So how do I represent? Outermost shell is called what? Valence shell. And the electrons present and the inner shells which are completely filled are called what? So this is valence shell. And this is what? This is core shell. Inner core shell, completely filled shell. Similarly, this is inner core shell, completely filled. This is valence shell. Inner core shell represents how many, which electronic configuration? Look at the electrons, you'll get to know. 6 plus 2 plus 2, 10. That means it represents neon. So how do we write condensed electronic configuration? Writing noble gas configuration into the box, writing the atomic number here and representing the valence shell over here. So magnesium condensed configuration, I can write it as, what is noble gas? Which one noble gas we have considered here? It is neon, because there are 10 electrons in neon. And outermost shell 3s2. Similarly, how will I write aluminium? 13. It is again neon bracket 3s2 3p1. Got it? So this type of configuration is called condensed electronic configuration. This was not discussed by me in the previous video. So I stopped it there only. So this is condensed electronic configuration. This is what? This is complete electronic configuration or just electronic configuration. Complete electronic configuration. Got my point? Complete electronic configuration. Understood? So condensed and complete electronic configuration. Even for condensed electronic configuration, why we use condensed electronic configuration is it saves our time and length also. See, simply sitting and writing all this, you can write just neon. Even you can write the orbital diagram also for condensed. So I'll write this like this, 3s. So I will represent a box, write 3s2 here and show the 2 electrons. For aluminium, how do I write? Noble gas core configuration, I will write it here, 10. Represent 3s box with 2 electrons. So spin up, spin down, and 3p box with 1 electron. So 3p1. This is how we write the orbital diagram. even for complete as well as for condensed. Yes. So complete and condensed electronic configuration. Now, causes for the stability of completely filled and half filled subshells. If you look at the completely filled and half filled subshells, they are very stable. Just now we looked at some of the examples. I'll show you which examples have completely filled. Okay. If you take example of neon, atomic number is 10. How do we write the configuration? 1s2, 2s2, 2p6. Orbital diagram, spin up, spin down, 2s, spin up, spin down, 2p, spin up, spin up, spin up, and then spin down, spin down, spin down. Correct? So if you see here, all the orbitals are completely filled. So we call this as completely filled subshell. Completely filled. One more example, if you take the example of nitrogen. Nitrogen atomic number is 7. 1s2, 2s2, 2p, 4. Sorry, 2p, 4, and here 3. So let us see. Spin up, spin out, 1s. Spin up, spin down, 2s. 2p, 3. Spin up, spin up, spin up. If you see this orbital, it is half filled. Half filled. Yes. Such completely filled orbitals or half filled orbitals, they account for extra stability. They account for extra stability. They account for extra stability. Now, why they account for extra stability? What is the reason? There are these reasons. If you see, if they are half filled, exchange energy comes into context. First one is symmetrical distribution of electrons. When they are half filled or completely filled, there will be symmetry in the distribution of electrons, right? Rather, if I write it like this, suppose there is P subshell, this is half filled, correct? And there is one more P subshell which has like this, or say it has like this electrons. Understanding? So here there is no symmetry, but here there is symmetry. Similarly, in case of completely filled also, I shouldn't write it like this. I'm sorry. Yes, I have to represent it like this. Or which is more symmetrical? Which is more symmetrical? This is more symmetrical. So there is symmetrical distribution of the electrons. It is well known that always symmetry leads to stability. In this universe, every minute of the minute to the large of the large substance tries to attain symmetry so that it becomes a stable. So the completely filled subshells or the half filled subshells, they have symmetrical distribution of electrons in them and are therefore more stable. So electrons in the same subshell have equal energy but different spatial arrangement. So when you consider the electrons in those subshells, or they are called degenerate orbitals, right? Because they have got same energy. Here 3D d orbital is being shown. There are 5 orientations, 5 orbitals, right? All those 5 orbitals will have same energy. But what is different? Spatial arrangement is different. Yes or no? dxy, how it is present? It is present between the two axes, x and y. dyz between y and z. dzx between z and x. dx square x y square on x and y axis. Yes. So spatial arrangement is different. Consequently, there will be protection of one another, shielding of one another, and is relatively very small. Relatively very small. And the electrons are more strongly attracted by the nucleus. So that is due to symmetry. So first reason is symmetrical distribution of electrons. The completely filled or half filled subshells have symmetrical distribution of the electrons in them and therefore they are more stable. Second point is the exchange energy. Here the second point is exchange energy. Now, what do we mean by exchange energy? What do we mean by exchange energy? See, here when there is symmetry, that is when the electrons are half filled or completely filled, they can exchange their positions. Can you see this electron can go here, it can go here, it can go here, it can go here. That means it can replace that electron to this place. Yes. Similarly here, second electron, it can move here, here, here. So three exchanges are possible by electron 2, two exchanges are possible by electron third, and there is only one exchange by electron 4. So what does this exchange energy come from? The stabilizing effect arises when two or more electrons with the same spin are present in the degenerate orbitals. Yes, these electrons tend to exchange their position, and the energy released due to this exchange is called exchange energy. What it is called? Exchange energy. The number of exchanges that take place is maximum when the subshell is either half filled or completely filled. If the exchange energy is more, stability is more. So when exchange energy becomes more, when more exchanges are possible. And when more exchanges are possible, when the orbitals are either half filled or when they are completely filled. Only that time exchanges are possible. Yes. So therefore what will happen? The exchange energy is maximum and the stability is also maximum. Stability is also maximum. Yes. So stabilizing effect arises when two or more electrons with the same spin are present in a degenerate orbitals of the subshell. These electrons tend to exchange their positions, and the exchange energy released due to their exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As the result, the exchange energy is maximum and so is the stability. Yes, and so is the stability. So this is about the extra stability of half filled and completely filled orbitals. Because of this extra stability of half filled and completely filled orbitals, what happens, in some cases there are exceptions. The exceptions are these exceptions. So we'll just try to see what are these exceptions. We know that when you're writing electronic configuration, we follow Aufbau principle, Pauli's exclusion principle, Hund's rule of maximum multiplicity. But because of the extra stability of half-filled and completely filled orbitals, there are certain exceptions in the electronic configurations of a few elements. To understand the extra stability of those exceptional elements, we will try to write the electronic configurations here. Okay, we will try to write the electronic configuration. Okay, so which elements I'm going to discuss now is I am going to discuss regarding transition elements.